In this lecture, we'll explore databases from a theoretical and practical point of view. We'll dive right into MySQL to do some actual SQL, and then look at how we can normalize and represent our data. A database is just an organized collection of data. We can visualize it as a file that holds tables, and those tables are made up of columns and rows. If you can imagine opening Microsoft Excel and looking at the main screen there, you would see a table, a tabular format with columns and rows. You would have fields. That is what the inside of a database looks like. And a relational database is just an organized set of those tables. So those tables working together will give you a relational database. A DBMS or RDBMS, Relational Database Management System, is an application that allows us to interact with the database. So it allows us to create tables, to update those tables, and just basically to administer the database. SQL is the language of databases. Think of an application, think of a program, most likely it's using SQL or some form of SQL. And when we talk about SQL statements, and we'll define these better as we actually do some SQL in the next part, but SQL statements can be divided into DML or DDL statements. So let's dive right into MySQL to have a better understanding. This right here is the MySQL shell, and this is integrated into my app. So as you create apps, you're going to want an environment like this, or you're going to see an environment like this where you can update your tables or check your database manually. And so any app that you create will have some kind of environment like this. So let's go ahead and get started. The very first thing I want to do in this is see if I have any tables in my database. So I'll use the DML statement show tables. And remember, DML is all about the data itself, so it's updating a table's data or inserting or querying. This is a query, so this is definitely a DML statement. And DDL is I kind of think of it as a more serious statement. It's dealing with the actual structure of the database itself, the definition of the database. So actually creating a table, dropping a table, these are all examples of DDL. But I'll keep clarifying this with every statement. So this is the DML statement, show tables, nothing happens. Let's go ahead, or it returns an empty set. Let's go ahead and say create table, and we'll create our first table called users. And notice how I declare all of this. I start a pair of parentheses, and this indicates that I'm getting started with my columns, so my attributes in my actual table. And the very first column will be the user ID, and this has a type of int, 9 bytes long, okay, of length 9, so it's an integer. And I want this to be my primary key, and I'll define primary key and foreign key and all these terms in the theoretical or the theory side of this lecture in the second part. But I'll kind of explain it here so that you can see it practically before you see it in theory or get the actual definition of it. But this will be the column that every other column depends on in this table. Primary key, and then we'll do something called auto increment. And all this is doing is this is saying as we add new users, or as a user signs up for our account, they're given an ID that's just one up from the last one. So if the last user was 5, the next user will get 6 automatically, and MySQL manages that for us, which is a nice, easy, simple method for us to use in this example. And then we'll go ahead and say user email, and this will be a varchar 50, variable character 50, and this will be unique. We need to have unique in here because we don't want to find that there's user 2, 3, 4, 5, and 6 with the same email. That's not good practice, so we want to make sure we make that unique. And then finally we'll have a user password. This will be varchar 50, not an int. You don't want to make a password an int. Varchar 50, and that looks good. So I'll go ahead and close that with this, close the first pair of brackets, and then end it with a semicolon. Make sure that looks good. Yes, and now we can go ahead and try show tables again, and we do have a table called users. Great, so let's go ahead and insert some things into our table. Insert into users value. So this is the syntax for inserting, and the very first value will be null because that's the auto increment, so this will become 1 automatically. And then we want bob@bob.com, and the password is 123. Great, make sure that looks good. We've inserted it. Press up to go back to the previous statement, or any previous statement, and let's add John to the database as well. The same password, doesn't matter. And there we go. Now I'll go ahead and say show tables. There's our table, and then a very nice DML statement called select all, or select something from a table. Select all from users. We can see that, and just to show you what select can do, I can also say select user ID from users. I can just get the user ID. You can specify user ID, comma, user email to get just those two columns, etc. And then you can do even a query here. You can say where user ID is equal to, let's say, just say 1, and that returns only the 1. And then I can say select all from users. So you can just play with these and get a basic idea of how it works, but this is just a quick overview of the syntax of select. Okay, great. So now we have those in our user table. Let's go ahead and create another table called courses. And this will have a course ID, int 9, this will be our primary key, and this will also auto increment. Let's do a course name, this will be a varchar 50, and it should be unique. Okay, great. So now we have this, and insert into courses, values, null, and intro to databases. Okay, and then intro to Python. All right, so select all from courses. There we go. So just to recap, DML, 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 DDL. So far, hopefully that's making sense. Okay, so now we want to do, or I want to show foreign keys is the last part of this. So foreign keys are, it's a column in a table that links to another column in a different table. Usually the primary key, but in this case we're going to make a table called enrollments and link that to the user email and to the course. So in any case, like Bob, for example, could enroll in this course or this course. So it's a many-to-many relationship in that table. So let's go ahead and create that table. Create table enrollments, and this will have an enroll ID, and this will be int 9 primary key auto increment, and let's do the course. Okay, so this is where it gets interesting. So we have the course ID. Now what I want to do is I want the enroll user email to be the column that has the user's email. And so I'll just create these columns as normal, but they have to match the original one, so, or the one in the other table. So varchar, it was 50 and it was unique. So that needs to match. And once I've done that, I can create my second column, which is the course name. We're going to use a course name in this case. And again, it has to match. So it was varchar 50 and it was unique. Great. So now how do we make that foreign key reference or link? We say foreign key, and we call the column that we are referring to, or we're talking about. And then we reference, so it says, you should write references, the table's name, so this was user, and it was, or users, and the column was user name, wasn't it? So let's go back and check. Oh no, it was, I'm sorry, it was user email. So there, we have that now referencing the users table, and the email, the user email column in that table. Okay, great. So that should match. There we go. Okay, great. So just want to double check these. And then again, foreign key. Now this will be the next column, which is course name. So we want to go ahead and change that to course name. Enrollment course name. And this references the courses table and the course name in that table. Course name. Okay, double check or triple check everything, make sure it looks good. Close our statement. Let's try it. Hopefully there's no errors. Great. And I'll show tables, see if it's been created. It has been created. And so let's try something. Let's go ahead and say insert into enrollments, and we're going to put some values. And the very first value will be null, obviously. Should be using capitals here, but so null, and the email is Bob, the user is bob@bob.com, and the password is, not the password, I'm sorry, the course is intro to databases. Okay, so let's see if this works. Okay, great. We have that going into enrollments. Select all from enrollments, and there it goes. We find out that it worked. Now, let's try something. Let's try to put in Sally@bob.com. So Sally doesn't exist in our database. So let's see what happens. We get a foreign key constraint. So this means that there's an issue with the foreign key. And obviously the issue here is that Sally doesn't exist. So there's some kind of problem between the foreign key and the link to the table or column that it's linking to. Okay, so now that you've seen SQL, we can now talk about some of the theoretical things behind what we did. Now we saw a primary key, we saw a foreign key. Let's define it and let's really break down how we can organize this data before we go and write the actual SQL. So the very first thing we want to look at is something called normalization. And the example I give is the example of a watch. If you have just one single watch, you're going to be, the chances of you arriving on time or that watch is correct is going to be greater than if you wore 50 watches. Because if you wore 50 watches, you have to manage all of those watches. One watch is going to die, the battery is going to die, one's going to be delayed. You know, you never know. So wearing 50 watches is not going to make you arrive anywhere on time, more so than just having one watch. So that concept of reducing redundancy is what normalization is all about. And in databases, you don't want to have redundant data, because if I want to delete a user from a database, I should be able to delete that user one time without having to delete them from a million places. So it's very important that we normalize our data. And to remember normalization or the different forms of it, we can remember this little expression that says that data depends on the key, the whole key, and nothing but the key. So let's understand what that's all about. First normal form is the first check that we can do on our data to make sure that it's going in the right direction. And the two conditions of 1NF is that each row must have a unique value, in this case a primary key. So every row must have a primary key, and cells must contain atomic values. And an atomic value is a value that cannot be divided. So let's look at an example. Here I have a table with user ID, first name, last name, email, and address. So this looks good. We have a user ID, a first name, last name, email, okay? But then look at address. Address is made up of a street, of a city, of a country, and this is not an atomic value. We can divide this field into 3 fields. So if we were to follow the practice of databases, you would want to have address as its own table. Okay, in the next example, let's say that an app does allow us to have 2 emails. So here we have an email field, but in that email field are 2 emails. And so that's not atomic. We can divide those into email 1 and email 2. Okay, so now let's say that we come up with the solution and we say, well, instead of making email 1, email 2, we want to just go ahead and say user ID 1 and repeat it, and we'll keep email atomic by making that have just 1 email, but then we'll just repeat the user ID again. Well, that's another violation of 1NF, because we're repeating the primary key. And imagine this, when we talked about redundancy, imagine this. Imagine Tremolini's last name changes, or something, we misspelled it, or something happens. How many times would I have to change that last name? Well, I would have to change it in this case twice. Not a big deal, but imagine if this was happening over and over again. So that's another problem, another violation of 1NF. Before we move on to 2NF, let's go ahead and define what a compound key is. In the last example, we had a user ID as a primary key, and that's what every column depended on, but it was a single attribute, a single column. A compound key is a primary key consisting of 2 or more columns, or 2 or more attributes. So let's look at an example. On the left-hand side, we have a composer ID with the name of the composer and the country. And on the right-hand side, we have the track ID and the track name. So imagine this fictitious award that is given to a composer, but only regarding the track that they've composed. So Hans Zimmer composed A Small Measure of Peace, and he got X awards. And then we had James Horner compose the Titanic theme, and he got Y awards. And then James Horner did the Ludlows, and he got Z awards. Okay, great. So what's happening here is a word does not depend only on composer ID. Otherwise, it doesn't make any sense. And a word does not only depend on track ID, otherwise it doesn't make sense. It has to depend on both of those, because both of those are the primary key, or the compound key. And that's what 2NF is all about. 2NF is all about removing any partial dependencies. And that's where that expression comes in. The data depends on the key, the whole key. And what this is saying is it has to depend on the entire key, not just a part of it. So a word must depend on both of these, not just a part of it. Otherwise, you'll have an issue, and you have a violation of 2NF, and you know that your database needs some restructuring. Before we move on to 3NF, let's go ahead and define what a transitive dependency is. And the best way to explain this is through this table here. So we have a composer ID and a track ID. We have a movie, a label, and a website. And we ask the question, does movie depend on the primary key? Yes, it does. Does label or website? Well, there's a potential problem there. Because if we change label from Warner to Turner, for example, website would also need to change. So website is linked to label more so than it's linked to the composer, the track ID. So that right there is a transitive dependency. It depends on label. So if we change label to Turner, the website would have to change. So website and label are definitely a problem, and we would have to remove those and potentially make a new table for them. So 3NF is all about that. It's about removing the transitive dependencies. Before we move on to BCNF, let's go ahead and define what a functional dependency is. So in this example, I have a user ID, a user email, the street zip, course code, course name, and the course grade. Okay, we can create some functional dependencies out of this. We can say that user email is functionally dependent on user ID. We can say that user street and user zip are functionally dependent on user ID. We can say that course name is dependent on course code. And we can say that the course grade is dependent on the user ID and the course code. So these right here are 4 functional dependencies that we've defined from our database. And when we've done that, then we can understand BCNF. So look at our dependencies. We have user ID for the user email. We have user street and user zip dependent on user ID, etc., etc. We have to ask the question. On the left side, in this case, the IDs in bold, these are keys. Is every left side of the functional dependencies a key? If the answer is yes, then your data is in BCNF. It's not in violation of it. If not, if something on the left-hand side is not a key, then you are not in BCNF. Now we move on to ER diagrams, which are diagrams that allow us to visualize how entities or tables are related. So let's start with entities. An entity is just a thing in a database. So students are a thing, students are an entity, courses are a thing, courses are an entity. And between those 2 entities defined in a rectangle, we have a relationship. And this is a rhombus symbol, and it says that students enroll in a course. And you can do this for any 2 entities. Think about it. A instructor teaches a course. Whatever you can come up with, you can find a relationship for it. And then attributes are the fields or the columns in that table. So imagine that the student table would have a student ID column, it would have a student email column, it would have a student FName column. And so we've defined these as attributes in our ER diagram. And I've underlined the primary key just to ensure that we know that that's the primary key in our table. Cardinality shows us the number of occurrences of one entity in relation to another. So I've given 2 examples here. Let's look at the first example. Person is an entity, child is an entity, and the relationship is has. We ask the question, does a person have to have a child? No, it's optional, right? They don't have to have it. So on the right-hand side next to child, you see a 0 or an optional looking symbol, and that means that the person doesn't have to have a child. It's optional. But if they do have if they do have children, they could have many. So 0 to many is the relationship on that side. Going back the other way, child to person, well, if a child exists, there has to be a person behind them. So a child has to have at least one person, but there could be many people behind them in guardianship or whatever. In the second example, we have mother. Now, a mother has to have a child to be a mother. So a mother has to have at least one child, or she could have many children. And then the other way around, a child has to have at least one mother, and usually they only have one mother, so one and only one mother.